As I see it, there's 3 reasons why Mars should be the goal of our space program. And in short, it's because Mars is where the science is, it's where the challenge is, and it's where the future is.
Pursuing this work, because I believe if we don't, we will eventually end up with a civilization of stasis. Stasis would be very bad, I think. Now, take the alternative scenario where you move out into the solar system. The solar system can easily support 1 trillion humans. And if we had 1 trillion humans, we would have 1,000 Einsteins and 1,000 Mozarts and unlimited, for all practical purposes, resources from solar power and so on. Why not? That's the world that I want my great-grandchildren's great-grandchildren to live in.
Was the most important thing. I mean, I think people would regard living on Mars as...
No, that's the relatively easier thing. Yes, absolutely.
So we could live on Mars, just getting there is the problem.
Yes.
So, like Elon says, living on Mars would be the relatively easy part. And we could take his word for it, but let's explore that a little further by looking into extraterrestrial construction. Particularly, some of the challenges, technologies utilized, and several concepts for habitation. I'll focus on the moon as it is seen as a stepping stone for further space exploration and colonization. Humans have traveled to the moon previously, which allows for the conversation to not be dominated by logistics. Rather, we can look at some of the more specific construction challenges that arise. With that being said, let's get right into it. One of the challenges has to do with temperature. Temperatures on the moon can fluctuate from -233 to 123 degrees Celsius. This large fluctuation is problematic as all structures, materials, and equipment not only need to withstand the extremes of this temperature range, but also the fluctuations themselves. Another challenge is that, unlike on Earth, the moon has no atmosphere to provide protection from dangers such as radiation and meteoroids. Due to this, habitation designs not only need to adequately shield humans from the high levels of radiation, but also need to withstand the potential of a micrometeoroid colliding with the structure. Related to meteoroids is an example of a challenge that's a little bit unexpected, and that problem is lunar dust, which you can see being kicked up as this vehicle rides around. Lunar dust is extremely fine, abrasive, and it sticks to everything. It's very difficult to remove and has a seemingly disproportionate impact on all activities on the moon. You can see how this dust adheres to a spacesuit, for instance, in this photograph from the Apollo 12 mission. Having gone over the primary challenges of building on the moon, we can begin looking at some habitation concepts and applicable construction methods. Concepts, like the one pictured, are heavily dependent on resources from the Earth. The habitation modules are either fully integrated prior to being transported or comprised of prefabricated components that are assembled on the moon. These methods, however, are ultimately not sustainable due to their dependency on Earth's resources. This may not be critical in the short term, however, for prolonged missions, large construction, and missions to planets far away, such as Mars, it is not viable to be primarily dependent on resources from the Earth. Due to this, the use of local materials is a significant area of research within extraterrestrial construction. This is commonly referred to as in situ resource utilization, or ISRU. This makes total sense. Just like terrestrial construction, if you use local materials, things get a lot cheaper. As I explain this further, let's take a quick trip to the moon, courtesy of the European Space Agency. There, we'll be able to see a concept for extraterrestrial construction. So as far as ISRU and extraterrestrial construction goes, rather than replicated traditional terrestrial construction methods that are heavily dependent on humans, what appears to be most promising is utilizing sintering-based additive manufacturing. So let's break that down. Sintering is the process of heating a porous material below its melting point so the particles can bond together and form a continuous, solid material. The additive manufacturing part comes into play when you put this into practice. So what this would look like is that a special 3D printer would be attached to a robot. The robot would go around and pick up lunar regolith, which is all the loose, solid material on the surface of the moon. This material would be combined with a polymer, which could be sourced from recycled plastics or directly from Earth. Together, this would form the printing feedstock. From then on out, just like any other 3D printer, thin layers would be printed on top of each other, allowing for the construction of, well, just about anything. Whether building a habitat or launch pad or roadway, this technology is very flexible. And since it's about time to land, we'll be able to see how this could all be applied. In this concept, after landing, a habitation module is unloaded. This is a fully integrated module that contains an inflatable membrane, and it will ultimately serve as the airlock for the structure. 2 robots are also deployed from the lander, and they are tasked with printing the primary structure from the lunar regolith. The inflatable membrane serves as a scaffolding for this process. Now what's really cool about this concept, and it speaks to the strength of this technology as a whole, is that it's fully autonomous and allows for a habitat to be constructed prior to humans landing on the moon. This is not only a lot safer, but allows for the astronauts to have all the necessary support structure that they need as soon as they arrive. Having talked about some of the fundamentals of lunar construction, I would like to bring up Mars in order to highlight some of the similarities in the technologies and approaches that are being developed. A great showcase of this is the NASA 3D Printed Habitat Challenge. As part of a series of centennial challenges, NASA and some of its partners put together a $3.15 million competition where teams set out to build a 3D printed habitat designed for Mars. The final phase of the competition involved autonomously printing a 1/3 scale habitat. Expectedly, ISRU is a big emphasis of this competition. Therefore, teams utilize indigenous materials and recyclables in their designs. The winning team, AI Space Factory, developed a thermoplastic reinforced with basalt fibers to serve as their printing feedstock. Their proposed habitat, Marcia, has this unique upright cylindrical shape. This shape was selected as it is an effective pressure vessel, it allows for an efficient floor layout, and it is feasible structurally and in terms of constructability. Speaking of construction, rather than using autonomous robots, a single, large stationary printer is used. Nonetheless, the same principles as discussed previously are followed. Thin layers of material are centered together with prefabricated components, such as windows, being intermittently incorporated. Ultimately, why I bring this example up is that it speaks to a larger point. That point being that extraterrestrial construction research, like all other space research, is highly relevant to everyone on Earth. And this goes beyond futurist perspectives. Rather, the science involved is directly applicable to today's society, right here on Earth. Using 3D printing technology in construction is very practical and allows for immense capabilities in terms of efficiency and speed, all the while unlocking new design possibilities that would not be practical when using traditional methods. AI Space Factory capitalizes directly on this as they pursue developing Terra, habitats for Earth that are inspired by their Martian counterparts. They plan on using the same printing technology, and given that their printing feedstock is fully recyclable, it is said to be very sustainable. This innovative technology, developed to be applied on Mars, has the potential to revolutionize the highly wasteful construction industry here on Earth. If such methods are tested and proven to work, it would be highly beneficial to the environment, and thereby all of us. This is all the result of what happens when human ingenuity is pushed to its limits, past the constraints of our Earth and into the unknown. There's much potential in all of this, and I'm very excited to see what will come of it in the coming years. If you would like to learn more, I would recommend the following papers to begin your further research. I'd also like to take the opportunity to thank Dr. Ramesh Malla, professor at the University of Connecticut, with whom I had the opportunity to speak to about lunar construction. He has been studying the subject for over 30 years and currently leads a team of UConn researchers working as part of the Resilient Extraterrestrial Habitats Institute, which has been tasked by NASA to develop resilient deep space habitats. And with that, I'd like to thank you all for watching.